Hey everyone, good morning. How are you doing? Great. Thanks so much for joining us. I know it's early in the morning, but we have a full day packed of really exciting technical and non-technical talks from the Ethereum Foundation. And we will start with Zsolt Felfoldi from the Get team. He's been with the foundation for a very long time, and he will be talking about a new approach of scaling layer 1. So please give him an applause.
Okay, hello everyone. So what I'm going to talk about is an engineering project that turned out to be turned into an R&D project, and now I would like to make the case that it might even be relevant for scaling Ethereum with the new storage architecture. So so this is where the story started. Last year, I started working on a new API. So this is one of the Go Ethereum team projects. The old JSON RPC API is very obsolete, and also actually it has never meant to be used the way it is used. What we started to work on is a new REST API that is similar to the Beacon Chain API, and provides all the responses with Merkle proofs based on the latest execution block hash. And so this is where the whole story started. But unfortunately, there are certain things about the chain that are not so easy to prove in an efficient way. Most prominent is the logs. So originally we had the Bloom filters, headers, but that wasn't very effective to begin with, and now it's practically useless. So right now, if you really want to prove the results of the log query, that basically takes the entire receipts, so like it's prohibitively expensive. Also, there is no easy way to prove that old canonical block hashes and transaction inclusion, or more notably, the exclusion proofs are very hard. So it's really hard to prove that something is not on the chain. So yeah, I just wanted to make everything trustlessly provable. So yeah, this is where it turned into R&D. Actually, the trustless log index project, it started out. So now, actually, this is what I have now is the third iteration. The first EIP 7745. That's like very complex, and yeah. Now I explored like different paths, and this is what I currently have. So it's based on what I call index tables, and these tables are generated from generated for every block, and then these tables can be merged together to bigger blocks. It's basically a sorted list of events, and yeah, it's just don't have a lot of time. I just quickly show how it works. So this is the most typical thing as an exclusion proof. So if something is not present, then there's a sorted list and there's a position where it should be. So proving the two adjacent entries proves that a certain, like in this example, a certain transaction hash doesn't exist. And yeah, there's a more complex example which I really don't have time to talk about now, but it can also prove like complex log pattern searches. And the way these tables are handled for like an entire chain history is that one table is generated for every new block, and then these tables are merged together. It's merging sorted list is an easy task, and only the single block tables are generated during block processing. The bigger tables are all merged asynchronously, so it's a really efficient thing, and so in this proposal the block header includes hashes for like 1, 4, 16, and 64 block tables, and bigger tables can still be generated, and the proofs get more and more efficient if we have bigger tables. But these can be generated with ZK proofs, so that this whole process is not a huge burden on the block processing. Yeah, so this drawing is kind of similar. It just shows like a comparison of log and state as like general storage architectures. And so the state is one huge tree, and it has a big advantage that a witness of a certain item in a state has a logarithmic cost, but also it's already big and kind of hard to synchronize. And if we seriously want to scale L1 100 times or 1,000 times, then even with this state expiry and statelessness, it's going to be a challenge. So what I started to explore is whether the trustless log index could be used as a contract storage architecture. The advantages, the main advantage is that it's very cheap to add new entries, because basically what we process during block processing is just the events of a single block, so that can be sorted in memory and hashed in memory. So adding a state entry is already 5 to 20,000 gas, and it's pretty clear that if we scale the execution, so that can be scaled many times with block level access lists, and so there are good plans for scaling the compute, but the state cannot scale at the same rate as the compute, so the gas cost would probably increase even more, while with the logs and the trustless log index, a log costs, like, it depends on the number of topics, but a typical log like a transfer which has 3 topics costs 1,500 gas, and it's easily maintainable with when we generate the trustless log index. So on the flip side, the witnesses are more expensive. So we merge these tables to bigger tables and even bigger tables. So we have a roughly logarithmic number of tables, and all the individual proofs are also logarithmic. So the witness cost is more like a log squared. So. But otherwise, it's a really convenient data structure. It's much easier. I would say it's much easier to synchronize than the state, because the historic index tables, the bigger the table, the longer time it is unchanged. So once it's generated, it never really changes. It just gets merged into an even bigger table at a certain point. But for the big tables, this means that they stay the same for a very long time, and we don't have all the challenges that we have with syncing the constantly changing state. Also, we have time information, so they can be looked up in a way that so the contract can have kind of the expiry enshrined by in a way that it just doesn't look very far back in the history. And yeah, okay, sorry, just go back a minute. So, but yeah, so if we really want to consider it for on-chain use, then we have to do something with the log-squared witnesses. But the thing is that this might not be a problem in the future, because we already have an account abstraction API by Vitalik, which separates the pre-checks and from the main transaction processing, and it is possible to do all the signature authorization and witness verification off chain. So basically, there are transactions with separated witnesses, and they can be batched together with the ZK proof, and so the witnesses will never actually reach the chain. So yeah, that's. I think something like this, I can't say this is exactly how it will look in the future, but something like this will probably be necessary for post-quantum signatures also, because they are big. So yeah. And yeah, in the future, if this becomes realistic, then we basically could have the advantage of very cheap writes, as opposed to the currently expensive and increasingly expensive state writes. And yeah, I don't have time to go into all the details, but actually, this could be used. This whole structure could be used just like the state as a key value store. But I think that the logs they are just a more flexible data structure. They are parallel execution friendly. Like sets and lists can be represented in a way that there are no write collisions. It's also multi-chain friendly. So it's just because it has the time information. It's easy to prove the relevant events since the last update. So yeah, and finally, so this is how I think this whole infrastructure could look like. I won't say it's a simple thing, but yeah, maybe at a point something like this will be possible. So we have transaction batching provers, which help with the big witnesses and also maybe with big signatures. And then there are the logs. The very recent logs can be visible by the EVM directly. And then we have these tables that the protocol generates, and we can have further ZK provers which generate even bigger tables from that. And yeah, this can go back to the witnesses, and the table merging proofs can also be merged with the other ZK proofs recursively. And yeah, so that's it. Thank you for your attention.